Hi everyone, my name is Maher. I'm a student in the GEOG201 class, and today I'm going to be talking about the idealized model for global circulation. So if you'll join me here in this piece of paper, we can get started. So as you can see here, I have a model drawn out. This is the idealized model for global circulation. It does not take into account the tilt of the Earth. It's an ideal model. So let's start with the equator, the area where most warm air is in this model. The equator has the most insolation. So what we know about warm air is that it's rising and it's associated with low pressure. So we've established our first pressure band. This is going to be the equatorial low. Now, with this rising warm air, it's going to eventually get to a point where it can't rise anymore. It's going to do something interesting. It's going to diverge. Around 30 degrees, this air is going to crash back down as it gets too cool and form our second discussed pressure band of high pressure, and this is going to become called the subtropical high. At these points, the air is actually going to diverge again, going back towards the equator in this direction, and then towards 60 degrees in this direction, and likewise up here. So next up, we're going to talk about cells, first of three cells. So we have our convection cell from 0 to 30 here. And within that, you can see two cells that are being formed, the first of three. And we're going to call these the Hadley cells, two of them. Now, I want to shift to the poles. So when you have air coming down from these cool areas, it's going to be an area of, first of all, high pressure. And this area, or this air, is going to want to move to an area, to a warmer area. So it's going to go down this way and this way, both heading towards the equator. Now, what you see here at 60 degrees is that these forces are going to meet, these currents, and they're going to basically converge. So at 60 degrees, we have convergence. And what happens at convergence? Low pressure. So this is going to be our next band that we're going to define as the subpolar low. And that's going to be an area of low pressure. And this up here at 90 degrees with our high pressure is going to be called the polar high. So here we have that. So as we currently have it, we're at this 60 degree mark where this air is meeting this air in convergence. Now, at a certain point, this air is going to be forced at 60 degrees upwards in both areas. Pardon me for that, that is a 60. That I accidentally wrote 230, but that is a 60. So this air is going to be forced upwards, and it's going to get to a point where it goes to the troposphere, and it's again going to diverge. Now, what we're going to have here is more cells that are formed. So we're going to call this cell up here the polar cell. And right here, ferrule cell. So in a better view, we have all of our cells now named, and we have all of our pressure bands named: polar high, subpolar low, subtropical high, equatorial low, subtropical high, subpolar low, polar high. So that is a total of 1, 2, 3, 4, 5, 6, 7, and we have 3 types of cells. So I just want to make a correction real quick. When this convergence forces the air upwards and then diverges, this actually happens at the tropopause, which is part of the troposphere, but it's the boundary between the stratosphere and the troposphere. So at the tropopause, that's where it diverges. The next thing I want to discuss is get a little bit into surface winds. So it gets essentially a lot easier here because you have, with all these cells, you have the arrows showing which way the wind is going to blow. So let's start from the poles. This air is going to flow from 90 down to 60. And as we can see in the polar cell, this is doing the same thing. Next, from 30 to 60, from the subtropical high to the subpolar low, this air is going to flow from 30 to 60, and in the same fashion up here. Lastly, from 30 to the equator at 0 degrees, we're going to see surface winds blow like that, and from 30 to 0, like that, meeting at the equator here. Now, one of the things that really has to be discussed in relation to all of this is pressure gradient force. So we have at the poles and the equator two basically like vast differences in temperature, the equator being an area of extremely warm air and the poles being an area of very cool air. So we have rising air at the equator, rising warm air and low pressure, and at the poles sinking cool air. So basically these extremes are driving this whole system because pressure gradient force wants areas of high pressure to move to areas of low pressure to try to balance out this entire these differences. So yeah, pressure gradient force moves from areas of high pressure to areas of low pressure to attempt to compensate and balance these differences. Yep. And that is another view of this and pressure gradient force. So here I've drawn out a new idealized model for this because it was getting a little bit messy before, and yeah, I just wanted to start fresh, just sort of explain the global wind systems. So one of the things I have to talk about, and this sort of relates to the last thing I discussed in terms of pressure gradient force, is the Coriolis force. So because of the way Earth's rotating, the Coriolis force is going to deflect currents and wind a certain way. So Earth's rotating counterclockwise. So in the northern hemisphere, things are going to be deflected to the right, and in the southern hemisphere, things are going to be deflected to the left. So in relation to pressure gradient force, what was initially just flowing from high pressure to low pressure is now going to be deflected to the right in the northern hemisphere and left in the southern hemisphere, and this deflection is going to basically increase until the Coriolis force can equal out with the pressure gradient force. Now we're going to get started talking about some of these global winds. So with wind blowing down towards the equator from the poles, and the effects of the Coriolis force, we're going to see in the northern hemisphere this wind coming down from the east and being blown towards the right. So this air is going to go like that. If you're coming down from the North Pole, you're going to be going to the right that way because it's the Coriolis force and the fact that you are in the northern hemisphere. Now this global wind is going to be called the easterly, and it also occurs in the southern hemisphere. So coming from here, it's going to be another easterly, but it's going to be deflected left due to the Coriolis force because you are in the southern hemisphere, and that's the way that acts. The southern hemisphere. So again, easterlies, and they are named from the direction in which they're flowing from, so their origin, so easterlies. Now the next wind that we're going to talk about is winds moving from subtropical high to the subpolar low, and likewise subtropical high to subpolar low down here in the southern hemisphere. So in the northern hemisphere, we're going to see this Coriolis force deflecting right again, and the winds are going to look like this. And we're going to call these the prevailing westerlies because they come from the west. Now down here, subtropical high to subpolar low again, but instead, because we're in the southern hemisphere, these are going to be deflected left, and they're going to look like this. And we are also going to call these the prevailing westerlies. So the last thing we're going to discuss here in terms of these global winds are winds flowing from the subtropical high towards the equatorial low in the northern hemisphere and the southern hemisphere. So in the northern hemisphere, these winds are going to be again deflected towards the right, and they're going to look like this. And in the southern hemisphere, they're going to be deflected towards the left, and they are going to look like that. So subtropical high towards the equatorial low in both the northern and the southern hemisphere, deflected right, deflected left, and we're going to call these trade winds. So these trade winds are going to be called the northeast trade winds, based on where they originate, and these are going to be called the southeast trade winds. So here you have it, the easterlies, prevailing westerlies, southeast trade winds, northeast trade winds, prevailing westerlies, and the easterlies again. So here we have it, the final idealized model for global circulation. We're just going to go through real quick and talk about everything that we've discussed today. We have three types of cells, three types of convection cells: a Faro cell, polar cell, and a Hadley cell. So there's two of each of these, and we have our 7 pressure bands. We have the polar high, subpolar low, subtropical high, equatorial low, subtropical high, subpolar low, and then polar high again. And that's 7. Now we have our global winds. These are going to be the easterlies, prevailing westerlies, southeast trade winds, northeast trade winds, prevailing westerlies again, and easterlies again. Thank you for listening, and hope you enjoy the rest of your day. So I just want to thank the listeners for hearing me talk a little bit about the idealized model for global circulation. I hope you enjoyed it, and yep, thank you for coming.